போயிட்டு வந்துட்டேன். நான் சுஷ்மிதா வரேன். போயிட்டு தான் வந்தேன். அங்கதான் எல்லாரும் வந்துட்டு போறேன். அங்கதான் போறேன்னு போனேன். அவர் இன்னும் பார்த்துட்டு வரல போல சங்கர். அது இனிமேதான் போடவே ஆரம்பிக்கிறேன். இவ்வளவு நேரம் கரெக்ஷன்ஸ் தான் பண்ணுவோம். இப்ப வந்து ப்ரொக்யூர்மெண்ட்னு ஒரு போர்ட்டல் இருக்கு, கவர்மெண்டோட போர்ட்டல். அதுல போய் அங்க ஒரு 40 பக்கம் டேர்ம்ஸ் அண்ட் கண்டிஷன்ஸ், அப்புறம் அந்த பிஓக்யூ அதெல்லாம் வந்து லோட் பண்ணி பிடிஎஃப் ஃபர்ஸ்ட் கன்வெர்ட் பண்ணி மேடம் சைன் பண்ணியிருப்பாங்க. இப்போ பை திஸ் டைம் அதெல்லாம் ஸ்கேன் பண்ணி அதை பிடிஎஃப் அதில் லோட் பண்ணி இன்னும் நிறைய ப்ராசஸ் இருக்கு. இன்னும் 1.5-2 மணி நேரம் ஆகும். யூஸ்வலா வந்து ஃப்ரீயா இருந்தாங்கன்னா ஃப்ரீயா பண்ணிடுவாங்க. அவங்க லீவ்ல இருக்கிறதுனால நான் பண்றேன். பர்ச்சேஸ் தான் பண்ணணும். இது பர்ச்சேஸ்க்கு அவங்க இன்னும் பண்ண தெரியல. அதனால பர்ச்சேஸ்க்கு வந்து ஃப்ரீயா கொஞ்சம் ஹெல்ப் பண்ணுவாங்க. நம்ம டிபார்ட்மெண்ட்டுக்கு தான் ஃப்ரீயா ஹெல்ப் பண்ணுவாங்க. ஃப்ரீயா லீவ்ல இருக்கிறதுனால நான் போறேன். ரெடி பண்ணி கொடுத்துட்டேன்னா ஃப்ரீயா இருந்தாங்கன்னா ஃப்ரீயா பண்ணி கொடுப்பாங்க. ஃப்ரீயா இல்லாதனால இப்போ நான் பண்றேன். எனக்கும் சரி நம்ம கத்துக்கோமே அப்படிங்கிற சந்தோஷம். ஏன்னா எனக்கு என்னால முடியாது நம்மளும் கத்துக்கலாம் அப்படின்றதுனால
So Ghulam will start in 2 minutes, and I think you'll have about 50 minutes and maybe 10 minutes for questions. I'll give you a heads up about 5 minutes before your scheduled stop time. Okay.
Okay, thanks.
I think Pratik, someone's calling you. Who is back? Uh, is anyone outside? Can someone just check? Just get everyone in. Okay, it's 2:29 years, so let's get started. Okay, let's. I think. No, hopefully, I think people are no longer sleepy after a very heavy lunch. So it's a great pleasure for, I think now Ghulam is going to give us, Ghulam Shaifullah is going to talk about future-proof precision pulsar timing and the role of low radio frequencies. So Ghulam, please take it away.
Thanks. So my name is Golan. I'm a postdoc at the University of Milano Bicocca, and I'm also affiliated to the Italian Institute of Astrophysics and the National Nuclear Physics Institute for some strange reasons. Most of you, I think, know me as a postdoc who's working within the EPTA, and I also spend a fair amount of time working with the IPTA. But in the interest of not overlapping too much with the talk that's scheduled after mine, I'm going to try very, very hard to limit the things I say about PTAs, although that forms the vast majority of what I do. What I'm hoping to bring forward with this talk is a general overview of what makes precision pulsar timing so difficult, and how we are taking small but definitive steps in improving not just the confidence of the greater community in our results, but also our own understanding of how we can improve our assessment of our data, improve our analysis pipelines, and hopefully find some very, very exciting science on the way there. So, of course, I can't start a pulsar talk without giving a little bit of background on pulsars. I'm not going to dive too deep, but I have to flash up this slide mainly because of the person down there on the right-hand side of this slide, who I'm a big fan of, mainly for their amazing work ethic, which is why we know that there are pulsars around today. But most of you know pulsars as this rotating lighthouses in the sky, which are, for every rotation, it's going to send off a pulse, which if you have a nice fancy telescope on Earth like the GMRT, you can pick up a very interesting looking pulse. And you can stack hundreds of them, thousands of them, millions of them. And they have some very interesting properties in themselves, but also given their regularity, it leads to some it gives us the possibility of producing some very interesting probes of the universe, these pulsars, and we are hanging around in. It's going to be a bit heavy on jargon, so I think it would be nice to get some of the nasty words out of the way. I'm going to talk a lot about pulses or profiles or TOAs. They basically mean the same thing, and I think most people in the room are aware of this, but just in case you get confused, I typically mean one thing, which is the radio intensity curve per rotation, or average over several rotations. When this pulse is drifting around over every individual rotation, this produces a short. This looks like a short noise process, and that is what we call pulsar jitter. I will also call this red noise, or I will call a certain manifestation of long period power produced by pulse jitter, either jitter or red noise, just to make things a little more confusing. I'll often refer to things such as bandwidth, where I don't always mean the radio bandwidth or the bandwidth of the gravitational waves that we're looking at. But I will try to clarify which one I mean where. But when I do say subbands or subchannels, I'm very specifically talking about breaking down the observing radio bandwidth into smaller chunks. There'll be a lot of talk of dispersion measure, but again, just to make things a little bit more confusing, very often what I will really be talking about is fluctuations in the dispersion measure, which depending on which part of the analysis you're doing, we usually
So Ghulam, we lost you. Can you hear us? Hello, Ghulam, are you there?
what is the most likely
Okay, so,
expectation.
Ghulam, I think you got cut off last one or 2 minutes. So
Right. So can you tell me where I stopped?
I think you talked about dispersion measure, and you're going to say, if you talk about fluctuations in dispersion measure, I think then.
Yeah. Right. So yeah, so when I say dispersion measure, I will imply the fluctuations in it most of the time. I won't actually spend a lot of time in this talk talking about the column densities, which are what the total DM measures. What I'm more interested in is the difference around the average value of the DM. We often call this DM noise, or in enterprise notation, this is the DMGP, modeled as a power law. I'll come to that in a bit. The other jargony term that I won't really explain a lot is the template, by which I mean, if I were to take, so on the right-hand side of the slide, I have a bunch of pulses, all from the same pulsar, over 30, well, this is not over 37, from the same pulsar, and you can probably see that they're different for each averaged pulse. But if I were to average all of them together and produce the most common shape, that is what I tend to mean by the template. But there are variants of this, and this is also going to form a part of this talk. So another sort of disclaimer is that I have a slightly convoluted talk. It is split into 6 parts, but they all aim to address different issues that I deal with as a pulsar timer most of the times. So they aren't really fundamentally tied to PTAs. This is more about just doing good pulsar timing. And that's why I did not title my talk as a PTA talk, which, by the way, I'm sure you will hear a fantastic one a bit later this afternoon. Given our rotating pulsars, we can sort of assume that we have this fantastic Einstein clock in the sky, which is sending us a pulse every rotation. And then you can stack these pulses, put them together to give a prediction of when you think the next one will arrive. Given this is coming from a pulsar, we need to know the position and how fast this thing is moving in the sky, which is the astrometric properties, how fast the pulsar is rotating, whether it's rotating stably or not, and if it is hanging around in a binary. All of these will affect the model that we build for the pulsar. These tend to be the deterministic parameters, and hidden in here is again the dispersion, the mean value of which is fairly deterministic. But apart from these deterministic aspects, there are also these somewhat stochastic processes that are affecting the model, which in the frequentist part of our analysis, we don't usually talk a lot about. unless you are doing an analysis of the interstellar medium with pulsars, or you're looking at the red noise process itself. And those are dispersive delays, red noise or low frequency processes, which typically arise or we link to the pulsar jitter. So I guess most people in the room are aware of how pulsar timing works, but just a quick recap. Essentially what we want to do is we want to take our observed data, which are the green pulses, which are, we can take it almost for granted that they will arrive as a continuous time series. They will have their own variations and fluctuations and all sorts of effects encoded into them. We will take our model for the pulsar and produce a prediction, which will give us a polynomial model of when each pulse is expected to arrive. We plug into that a template for the profile shape, do some sort of cross-correlation between our template and polynomial model and the observed pulse stream. And that will give us a very nice set of times of arrival of the groups of photons in each pulse. And you can then you can take the same polynomial model, refit it to this set of TOAs, and improve the model in an iterative fashion. And I will come back to this in a couple of slides, but since I mentioned I spend a lot of time doing PTA stuff, it would be unfair to put PTAs in context, if only to give some definitions which I can lean back on further down the slides. So PTAs are just a collection of pulsars in the sky which are observed every so often. We love to observe them. We would love to observe them every day if possible, but typically PTAs observed with the cadence of anywhere between a week, 2 weeks, or a month. When you have collected enough data, which is about 20 to 30 years, you are uniquely sensitive to a window of gravitational waves, which is down there in the nanohertz range. Our sweet spot is actually bang on in the nanohertz range. As you can see that, sorry. Can you hear me now? Yeah. Sorry, I seem to be getting some broken audio as well.
Go ahead. Are you getting an echo? Yeah.
No, not now. I was just hearing a broken voice.
Maybe it was just me mumbling, but I'll try to mute it. Yeah, go ahead.
Okay. So yeah, but as I keep saying, I know there's a fantastic talk lined up on PTAs, so I won't dive too much into what PTAs are, except to point out with this little bar chart on the right that PTAs are situated in a frequency space that is not available to most current and proposed detectors, which makes them exciting for their own reasons, but also pretty challenging. So it doesn't matter whether you build a PTA or whether you take a single pulsar and you want to study it. The process is very iterative. Take a telescope, point it at the pulsar, get the pulses, de-disperse them, stack them together to increase your intensity through the process of folding. Take a bunch of observations over 40 minutes to an hour, stack them together to produce an average profile, cross-correlate with your favorite template, which will give rise to a bunch of TOAs, which when you apply the timing model will give you the timing residuals. If you do this for long enough and for a large enough number of pulsars, this is basically what a PTA is. PTAs, or pulsar timing in general, suffers from a bunch of noise sources. There are intrinsic sources of noise from the pulsar itself, issues with modeling the binary properties, the effects of propagation through turbulent ionized plasma, such as the interstellar medium or the solar wind, effects related to the sorry, I heard a voice again. Am I disconnected?
Yeah, you're audible now.
Okay, so yeah, PTAs have a bunch of noise sources. Sorry, is it clear now?
Yeah, please go ahead.
Okay, I think occasionally I'm getting some feedback of my own voice. But do feel free to stop me if you can't hear me. Right, so there are effects. The telescope from the recording hardware, there are issues. Sometimes there are issues related to the software. Sometimes there are issues related to the choice of models you make, and all of this eventually will creep into any statistical analysis you do, hoping to search for whether it be the stochastic background or the continuous wave sources, or if you're more interested in the pulsar itself, characterizing the properties of the pulsar itself. So a vast majority of my time is spent in cleaning up data, looking at TOAs, fitting models, figuring out what to do and how to do it better. And that's what I've been doing for about 2.5 years now, which is putting together the EPTA data combination 2.0. This uses data from 5 telescopes, and when they're all combined together, it forms a 6th one, which is why we tend to write the 5+1 notation. What we did was we took the EPTA DR1 and added to it data from a number of new instruments at each telescope, which gives us about 10 years of extra data. The good part about the new data is that we are doubling the bandwidth, the radio bandwidth at each telescope, and we use coherent dispersion with a much greater cadence. All of this boosts our timing sensitivity significantly. However, given the huge amount of data and the manual churning of the observations into TOAs and the time required, we can only process so many. So we've picked 25 of our best sources for various reasons, and that's the combination we will produce. We also have a non-priority list of 7 pulsars which are being combined for their own timing purposes. But the even cooler part about the second data release is that it will include the InPTA's DR1. This has already been done. We've already finished combining, and I won't tell the authors of the InPTA DR1 what the InPTA DR1 PTA is all about. But the really good part about adding the InPTA DR1 is that it gives us a huge boost in sensitivity to DM processes because of simultaneous ability of GMRT to observe at high and low frequencies. We currently have an overlap of about 10 sources between the EPTA and the InPTA, and we've just started a bunch of noise modeling, which I will talk about in a minute. Well, actually, I won't talk about the noise modeling, but I'll just quickly show you where we are at. So we have finished the combination of the data. What I'm flashing up here are timing residuals for 6 pulsars, 5 of which have in-PTA data combined. Essentially, the idea is that you can see that there's a lot of data to be combined, a lot of instruments that we need to individually probe and study and characterize and make sure things are all right. That's what has taken us almost a year to diagnose issues with one of our telescopes and figure out how to correct for it. Once those residual plots, these come with timing models and TOA sets. Once these have been produced, the timing models and TOA sets can then be tested using Bayesian methods to search for the stochastic signals, which, as I mentioned earlier, are the red noise process, what we call the red noise processes, and DM noise process, or the DMGP process. What we have done uniquely with the ePTA is that we've also done this test of not just analytically marginalizing over the timing parameters, so not just using frequentist plus Bayesian method, but then going back and doing a full Bayesian search over all, not all, but many of the timing parameters which we know co-vary with the red noise processes that we are adding with the Bayesian modeling typically. The good news, I'll briefly hint at the results a few slides down the line, but so far the good news is that yes, we've added a good amount of data, we've boosted our sensitivity quite a bit, very high cadence, and in most cases this leads to a sharp decrease in the timing residuals, but when the red noise processes start to dominate, of course, this shows up in strange and funny ways. So I haven't put in any goodness of fit measures here for the models. That is also ongoing work, but this is just a summary of what I just said. We have about 25 years of data, and for each pulsar bit, we are adding we are almost doubling the total time span, and in most cases, this does lead to very good timing performance. One of the things we do is we check whether our timing models are good, and the way we do this is by comparing the timing model before we started fitting to the timing model after, by looking at the residual plots. Here things look very good, but we find these strange outliers. Keep these in mind because I'll come back to talking about them in a couple of sections, and I hope it'll make sense that we're not really terribly frightened by the number of outliers we see for each pulsar timing data set. Of course, all this fuss about modeling red noise processes, about DM noise processes, I mean, why bother? Why bother adding in a bunch of different telescopes? Why, chase and harangue the in-PTA people into sending us data which we combine, and then we find more issues? Well, the problem is in the search for low-frequency gravitational waves, or if you're interested in, say, the gravitational waves from a pulsar binary, you want a fantastic timing model. But if your pulsar is going to show you drifts over tens of years, it is not going to be a fantastic timing model for searching for gravity or probing gravity. And the reason for that is that the kind of signals you're interested in is the low frequency one. And so is the intrinsic red noise process from the pulsar. And so is the DM noise process. So if we really want to characterize this, we need the sensitivity that GMRT will give us. We need the sensitivity that low frequency telescopes will give us. But at the same time, we also need incredible amounts of sensitivity to the radio emission itself, so that we are able to pin down high frequency variations or other sources of errors, other sources of timing model errors, which we also need the L-band and higher frequencies. So the way we deal with this in the PTA world, and increasingly even for individual pulsar timing, is to plug in the frequentist timing process, which is either you use tempo2 or pint, and you construct your polynomial models, and then follow this up with a Bayesian analysis. The need for this comes from the process I just described, that the GWP is a low frequency process, and it is kind of competing with a whole bunch of other sources of noise. Some of these are somewhat easy to say.
I think
to all your TOAs. So the most pulsar timing, this is the solar system barycenter. If that is incorrect and it's drifting around, then you will see a kind of dipole-like error. But things like the solar wind or the ionized, the excess delay that is being plugged in by variations in the solar wind, that can also mimic something like a dipole plus a monopole process. And all of this needs to be accurately modeled out if you are going to try to recover GWBs, the GWB or continuous wave sources, or if you're trying to characterize the behavior of, say, a pulsar binary where you are searching for GR effects. Of course, we haven't yet made a public release of the DR2. We are working very hard towards it. It's almost ready, but I'm not really able to show many results from it yet. Keep your eyes and ears tuned. It will appear in a month, and a bunch of very fun results have showed up, and it's been an interesting experience to get this done. What I can show you, though, is some preliminary runs I have done using some older data, which we published a while back. And I ran a bunch of searches, and along with some timing and different methods of generating TOAs, which leads to a nice agreement of the different noise models. Right. Sorry, I'm just occasionally getting this echo, which I think might be because of some feedback from the streaming process. But we've also spent a fair amount of energy in figuring out whether we are doing the right things, how to do things better, and that's what I mean when I say future-proof timing. And the need for all of this is we are tantalizingly close to the signals of interest. This is a plot everyone in this room has probably seen 1,000 times already. There is a common red noise process which is very, very likely to be the GWB, except we're not quite there yet. All the three leading PTAs seem to see the signal, and in work that is ongoing, we are also looking at improved sensitivity to the same signal, but to make that final step, a lot of effort is being put in, not just to improve the signal to noise of the signal of what we're detecting, but also in understanding our own detection techniques and methods, and whether or not we could be biased by this thing. So, as I mentioned a few months ago, we have already made an interim release of the EPTA DR2 using our 6 best pulsars, which led to the EPTA also recovering this common red noise signal. However, we do not find any evidence for the Hellingsdown correlations that we would want. So one of the things in the EPTA that we did, led by Anuradha Samajtar and myself, was this looking at whether or not we can improve our Bayesian methodology, because typically what happens is that we run these stochastic sampling or using mostly Monte Carlo methods, and getting Bayesian evidences out of Monte Carlo methods is non-trivial. So we wanted to verify whether the evidences that we report are reliable. So we compared stochastic sampling methods, such as nested sampling, with the traditional Monte Carlo methods, and we find that our noise models agree broadly, depending on the choice of actual sampling algorithms. But at the same time, it's very comforting to see that regardless of whether we choose nested sampling or Monte Carlo, we do tend to recover roughly the same signal without serious cause for discomfort. Another thing that we are in the process of doing is, as I briefly mentioned, we are doing fully Bayesian fits of the timing models, along with some testing. So on the left, I'm sorry about the watermark. Well, it's not a watermark, it's overlaid text, but this is really a preliminary work, and I've been cautioned very strongly to let people know that this is really, really preliminary work and not fit for sharing. But I did want to give you an insight into these steps. So the other thing we've verified is that the mixed method of analytical marginalization over timing parameters combined with a Bayesian search for the noise parameters is indeed reliable. It might look, so this plot on the left is actually an example of where things went wrong, but it had nothing to do with the actual timing process. It was more a question of setting up the analysis properly. And to really verify that these things work as we expect, the most stringent test you could do is to produce a parameter plot, or the PP plot, and what you expect is, if everything in your sampling procedure is perfect, and your parameter recoveries are recoveries of the truth, then in 90% of the cases, 90% of your samples will fall within the 1 sigma bound. Of course, this doesn't always happen, and it's really hard to do timing at that level. But again, when things are done properly, we can show that as far as PTA work goes, it is quite convincing, or the parameter plots tend to be quite convincing, and we don't really see a huge spread in the models. Again, the plot I'm showing you is from a preliminary run. This is not science-worthy data, so please don't read too much into this yet. But this slide is just to show you how much we are digging into not just our traditional methods, but also into every new thing that we've added over the last 10 years. Okay, this is a nice place to talk about traditional methods. So fundamentally, pulsar timing relies on using times of arrival, which is to take your pulse profile and convert it into a time of arrival at the telescope for the group of photons making up that profile. And the way we do that is through the cross-correlation technique. As I mentioned somewhere, we use templates, which are reference profiles for each pulsar, typically produced by taking a set of very good observations or representative observations of the pulsar, and then doing cross-correlation in the Fourier domain to produce this TOA and its associated error bar. There are a number of techniques to produce the TOA.
Ghulam, are you there?
Perhaps only one real technique. Newer Fourier domain with Markov chain Monte Carlo, which is an improvement on the PGS scheme, but it does lead to much better recovery of the associated error bar on the TOA. And there are also some other legacy methods which are not used that often, such as the Gaussian interpolation shift method, which works in the time domain as opposed to the Fourier frequency domain of the two previous methods. These are specially developed to time what low signal to noise observations, and also deal with issues of self-standardization, where you are unable to separate out the template from your observation itself. So one of the things that we've been looking at with Jun Wang and Joris Verbiest is to figure out what is the best choice of frequency bandwidth to put into a single TOA. This is because within the EPTA, we still do what we call frequency average TOAs. We are not using the fairly new method of wideband timing yet. And it turns out that our data are not particularly well suited to techniques like the wideband timing method. So we wanted to find out what is the best choice of, or how wide should I make my channels so that I have the best timing precision. So my TOAs have the smallest error bars, but at the same time, it does not hide the DM noise, for which I do need a resolution across the observing band. So we came up with a scheme to quantify the behavior of the TOA as a function of the observing of TOA bandwidth. And using this method, sorry, I'm still getting a lot of feedback. Right. And using this method, then we applied our TOA optimization algorithm to real data, and we find that it is not a straightforward choice. There is no simple analytical expression to describe the performance of TOA bandwidth or the precision of TOAs as a function of bandwidth. Rather, it is a telescope and observing system dependent feature. And the RMS of the TOAs, or the timing residuals, appears to decrease asymptotically. So it's not as if we can just keep adding more and more observing bandwidth and keep improving our timing precision infinitely. There is a certain noise floor, and I won't go too much into the details on this slide, but if there are questions, we can come back to this. But we find that, but the one thing we do want to take away from this slide is there is a preferred bandwidth for each pulsar given an observing system and a telescope that is being pointed at this pulsar. It also needs to take into account scintillation, which is the fluctuation of the observed intensity. Sorry, there's feedback again. Yeah, so we do need to account for scintillation as well, and this analysis kind of naturally does that. You can place a hard limit on the lowest frequency or the lowest bandwidth using scintillation. Right. And once we've done that, we can then compare the performance of the TOAs as a function of the cross-correlation algorithm as well. And we find that in general, the GIS scheme tends to perform really poorly. Template generation using a single bright observation is a really bad idea. And that's pretty much self-apparent conclusion, I would say. When you have pulse profiles which vary over time, choosing one to model the rest is generally a bad idea. We find that FDM is typically the best generally, although occasionally PGS will outperform FDM. I'll skip over this telescope because this is just related to the telescopes. So slide because it's related to the telescopes. A quick summary of where this reprocessing leads us is that it gives us much better constraints on the stochastic noise processes that we model, and allows us to recover very, very well-constrained posteriors for all of these processes. And sometimes when the traditionally processed data fail to detect signals, the reprocess method does, but at the same time, we do find sometimes things can go a little a bit in disagreement, and then we have to go back and investigate the actual timing models and the residuals to look at where these come from. Typically, these come from being able to separate out white noise processes even better, which again, I will quickly touch upon in the next set of slides. Okay, so this is all nice, but a little bit scary that you can alter things somewhat by changing your processing. And as I mentioned about 10 slides ago, there's also this problem of outliers in your data. Why is Golan not worried about outliers in PDA data? Well, that's because a student of mine spent a fair amount of time in investigating what is the influence of outliers on pulsar timing arrays. How bad does it get? Do we lose the GWB signal? We ran a fairly simplified analysis, assuming evenly spread outliers in some given IPTA-like data set. And then we searched for the GWB in it, which, surprise, surprise, was almost always recovered quite well. There is some drift in the recovered values as compared to the injected values. But in almost all the cases, we also find that it's often very hard to recover the red noise processes for these pulsars. We then redid the whole simulation, this time changing our data sets by increasing the sources of noise in each data set. We injected white noise, red noise, DM noise, along with the GWB, and tried to recover the same signal every time. We find that very often the failure of red noise recovery is driven by the level of white noise in the data set. We find that, there seems to be a lower limit on the number of low frequency bins required for a reliable recovery of the red noise process, which is about 6 low frequency bins. That means you can't have too much high frequency noise or white noise in the data, and have outliers in it. Which is, again, a little bit scary, that the red noise process becomes difficult to characterize. And this is bad for individual pulsar timing, but for the GWB, it's not such terrible news, because we always recover the GWB.
Okay. Hello, Ghulam.
Around which is pushing out the GWB, you become less sensitive to it. But ultimately, the recovery is not going to be taken away just by injecting a bunch of outliers. Okay, I'm going to sort of break everybody's train of thought by now talking about low frequency timing in the last few minutes, and showing you how you can use pulsar timing to, first of all, estimate the effects of the solar wind in pulsar timing, and then go back and correct models of the solar wind. This was a rather fun exercise to do, and we are still carrying on with this. The origin of this is, of course, that when you're observing pulsars, you don't have only the interstellar medium to deal with, you also have in between the solar wind. And the solar wind is not a simple beast. It's messy, it's complicated, it's time variable. But we do observe the sun very, very closely because it's close by. And what goes on the sun affects our daily lives to some extent. This has been tried before for pulsars. We're certainly not the first, we won't be the last. With a history as old as, somewhat older than me, in fact. But one of the most significant tests was carried out by Xiaoping Yu and Bill Coles, where they used PPTA data to try to improve the modeling using a two-phase model of the solar wind using magnetograms from daily optical observations, and then using some expansion techniques. However, that doesn't really seem to work that well, especially when you have data at 100 or 200 megahertz, as we did with Katerina in 2019 and 2021, where basically we use this technique of modeling the interstellar medium, using Bayesian approach, and then subtracting it off to get the total contribution from the solar wind, and then trying to compare that with predictions from the two-phase model of Yu et al., as well as some other comparisons. And we find that generally, given the level of variations and the issues with expansion of the models from the magnetograms, the 1 over r squared model often outperforms the biphase model, but at the same time, it does leave behind significant timing residuals at the typical PTA timing frequencies, sometimes as large as 20 microseconds. We can do a lot better than that, and there is ongoing work within the EPTA as well as the other PTAs to use the PTA data itself in very interesting ways, but I won't talk about that here, except to just briefly mention some people working on those. Sorry, I'm also sort of running out of time, so maybe I'll push on. Okay, so what we can also do is we can take the pulsars and use them as data sources for these models of the solar wind. So instead of correcting pulsar timing using a model, we take pulsar timing and correct the models. But typically for this, you need a bright source, which gives you a very high precision line. DM time series has a very convenient location because the solar wind, as complex as it is, there are some general rules about where you don't want solar source to be, which is typically towards the solar poles, or you don't want the line of sight. So spending a lot of over the solar pole. That's a region of high variability. So one of the things we did is to compare against an established technique, which is interplanetary scintillation, and where you observe compact sources, you observe their angular broadening, and you convert that into a scattering estimate. From the scattering estimate, you can then build up a density model. If you observe a bunch of these compact sources regularly, you can then use tomography to reconstruct a 3D model, assuming some behavior which is connected in time. So every time step is connected to the other by a set of governing rules. Things don't break down between time steps or between observation sets. And we find, as I show on this slide here, the IPS measurements, which are the points in black, line up without any real processing. So all we did was we took the estimates of the solar wind from pulsars and we plotted them against the estimates of the solar wind from the 3D tomography technique. And we find that they are usually in very, very good agreement, but also there are deviations on very short timescales. And this is something that surprised the IPS people. And we are now going to look into where these differences come from and where IPS is failing to provide an accurate model of the solar wind. The other thing you can do is you can take the similar to the Yu and Coles et al. Approach. You can take magnetograms of the data, and this time add in some from satellites. and produce and use the powerful machinery of 3D magnetohydrodynamic modeling to give predictions of what you think the density of the solar wind is and how it is evolving. Not just the density, but it is a full model which talks about everything that the solar wind contains: densities, temperatures, magnetic field strengths. But a lot of this requires good quality input data. You also need independent data sets to verify such models. So something we did last year was to do a proof of concept where we take one pulsar and we try to see if such a model can be tested. So the model we worked with is called Euphoria. It's a relatively new, fairly advanced 3D MHD model of the solar wind, and as I mentioned, it gives you not just densities, but also speeds of the solar wind, the associated magnetic fields, and any other quantity that you might be interested in, such as temperatures. What you can do is you can take the models for every time step, and we took 1 day time step, and we produced these full 3D models and compared them against estimates from pulsars. The way we compared them was to define a bounding box of about 2 AU, and within that 2 AU, extract the estimate from Euphoria using this smoothing technique, where Euphoria gives you a 3D model, and you can draw a line in the 3D model, convert it into a 1D profile. And then I smooth the 1D profile, convert that into an average, and using this Gaussian averaging process, I produce an average estimate along that section of the line of sight to the pulsar. And then I take pulsar DM estimates for the same days and compare them against predictions from Euphoria. So one of the things we found that
About 5 minutes more, if you can hear me.
Yes, I'm almost about to finish. Thanks. Right. So what we found was that while
Ghulam, can you hear us, Ghulam?
I can hear you, but the speaker has
Yeah.
no longer audible.
I think he got disconnected. Yeah. BCJ says we seem to have lost him.
Sorry, I just dropped out for a bit. Can you hear me now?
Yeah. We have lost your slides also.
Yeah, I'll put those back up. Can you see my screen?
Yeah. Let me just go screen.
Yeah. So so this picture with these green frills is a bit misleading, because what is actually represented here is a single density surface. And when you look at it in the single density surface or the isodensity surfaces, it does look like there is a big difference between the last day and the other 3 days that I've shown here. But when you look at the total maps, what you see are this maps like the purple and yellow one. So if you were to average up the density over the whole volume, you tend to get a much higher estimate. And the reason for this is that this dip feature, although it's modeled properly by Euphoria, the estimate is off because there is actually a coronal hole that is emerging in that region. And this can't be detected by Euphoria. So what we were able to do is to take our disagreement and then look at EUV data and show that there was actually a coronal hole emerging in the region where we have the strongest disagreement. And that was a nice and fun result to do, and it was also a nice proof of how sensitive pulsar timing is. So you will probably hear a lot of talk about solar wind models as well in other PTA talks, and how it limits not just PTAs but also precision pulsar timing. So we won't dive too much into it, but I just wanted to show that pulsar timing itself is capable of improving things quite a bit. So I'll leave the summary slide up, and if there's time for questions, I can take some questions.
Talk. Okay. So I leave the floor open to questions. So let me just ask the Zoom participants if they have any questions. So BCJ, Ramiz, and anyone else who is online. Do people have questions? Okay, so BCJ has a question. BCJ, do you want me to repeat, or you will?
If you can hear me, then I can say it out aloud.
Golam, can you hear?
Okay, so Gulam, the question is about the slide on the observation bandwidth for the time of arrival. So if you could just go back to that slide where you had these curves which were saturating.
Yeah.
Yes, this one. So I had two questions here. The first question was that the bandwidth may also be dependent on the local center frequency, right? So if you are doing the bandwidth at 300 megahertz versus the bandwidth at 1 gigahertz or 3 gigahertz, you may get different estimates. So is that correct, or I'm missing something?
No, you are correct.
Okay, because the scintillation properties will change as a function of frequency.
Yes.
So even the optimal behavior may change. So,
yes.
That was one thing. And the second thing is, this could be one factor for limiting the bandwidth, but what about profile evolution? So in some pulsars, like 2145 minus 0750, the bandwidth might be limited, or if you do a frequency resolved analysis, you might be limited by how much the profile evolves from one subband to another subband. So was that also what you people took into account in this analysis?
In this particular one, we have a natural way of dealing with profile evolution, especially for 2145, which is that we make templates for each subband. So we are in a sense frequency resolved, but as you can see from the plot right at the bottom, things don't just improve dramatically as we keep averaging more and more bandwidth, right? So right, so the x-axis is not really that visible. But what's on the x-axis is the bandwidth being averaged together. So as you average more and more bandwidth, profile evolution does kick in, and it's going to make things messy. So the hope is that eventually, when wideband TOAs are a commonplace thing, that will take care of these issues.
Okay, yeah, thanks.
You had another question, BCJ, right? You said two questions you had.
Oh, no, I asked both of them.
Okay. Anyone else online has a question? Okay, so anyone here? Yeah, I'll take them later for questions for you, the audience. Okay, so maybe Pratik, you can just read. So there's a question from YouTube. So yeah.
Yeah, hello, Golam. Can you hear me?
Yes, I can.
So this is a comment actually on since we are also streaming on YouTube from
Yeah.
Indrajit. He says, Golam, you mentioned low frequencies. How about 50 to 80 megahertz? Is it suitable for TOAs?
Well, 50 to 80 megahertz will not give you TOAs which are incredibly precise. But if you have 50 to 80 megahertz observations, you can do a lot of interesting pulsar science. Pulsar timing, however, will be limited, except if you have a high frequency instrument to be able to couple this with, which is why I said GMRT is a fantastic instrument to work with, because it gives you relatively large amount of bandwidth at 300 megahertz, and at the same time you're observing at 1.4 gigahertz, or a little bit higher if you want. And in combination, this is a fantastic instrument to work with. Just by itself, if you want to use 50 to 80 megahertz, you will probably be more interested in the effects of the interstellar medium or the solar wind. So those effects become really, really loud and clear at that band. But the overall TOA precision is still going to be a little limited. But as we've shown with LOFAR, sorry, I don't have a slide up for that. But if you look for papers by Donner et al., that kind of relative bandwidth at those frequencies is actually quite fantastic for looking at the interstellar medium.
Okay. Okay, so Avinash has a question. So quick, but you already passed 3:30.
So you have mentioned about the data is not suitable for wideband, right? So what exactly is the problem?
Well, the problem is, in a sense, the fact that we don't have a lot of collecting area. So when we try to add, or that's not completely correct. We are in Europe. We have a lot of RFI that raises our system temperatures quite a bit, which means that when we do the fine channelization that wideband TOA generation likes, then we don't get a lot of signal to noise in the individual profiles. This messes up things a little bit and gives you TOAs which are either as good or slightly worse than the normal narrowband TOA generation schemes. So we don't get a lot more out of wideband TOAs. That's the problem for the EPTA. Essentially, people.
Okay, so let's thank Ghulam again for a very nice talk. Okay, this shows the application of pulsar timing to many different fields. So he'll reconvene again at 4 for Maura's talk. So thank you all. So online participants, we were taking a break for about 20 minutes.
Sorry, Shantanu, I dropped out for a while, but I hope Avinash's question is answered.
20 minutes, we'll be back.